Hello, welcome to this unit test or study guide on acids and bases. Before we begin, I think it's important to note that up top on these slides, I have the title of a video on this channel that can help you answer these questions if, after I give you the answers, you find that they're just a little difficult. First question, the task is to sort these formulas and properties into columns, identifying whether they would match an acid or a base. Up first, we have the column for acids. So here we have a formula HCl. We know that this is an acid because it has an H out front, which is the only positive ion in this compound. Then acids are sour. Typically, we're talking citrus, lemons, limes, even pineapples are acidic. Acids are going to have a low pH. They offer hydrogen ions, like I mentioned, as the only positive ion when they dissociate. We have the fact that acids are actually covalent, which is a little weird because they kind of sort of have ionic properties as well because they dissociate into ions, but truly they are covalent. And because they're covalent, the vocabulary is a little bit different. When they're mixed with water, they don't technically dissociate. They actually are ionized by water, meaning that water kind of attacks them and rips them apart. And then finally, we have an organic acid down here. This is CH3COOH. This COOH typically is going to indicate that you're working with an acid. A lot of students will get this confused because it has the OH at the end, just like bases. But because this is covalent, it can tell you that it's not a base. It has to be an acid. It's just the structure for an organic acid is a little bit different. It's just this H that makes it an acid. This O and this O kind of stick when the acid is ionized. It's just that H that pops off. Now over here, when we talk about bases, we have the classic base example of sodium hydroxide. All bases are going to have that hydroxide and they will be ionic. So they will contain a metal ion unless we're talking about ammonium hydroxide. That is a base that has no metal, but it's still ionic. Then bases by their nature are bitter, kind of like a soapy taste. Not that you should be tasting the chemistry, but bases will be bitter. They have a high pH. Their pH is going to be greater than 7. They have hydroxide ions that appear when they dissociate in water, and they dissociate because they are ionic. For the next question on Bronsted-Lowry acid-base theory, you are asked to identify which reactant is the acid and which is the base. This should have been pretty straightforward simply because this is easy to identify the Arrhenius acid based on the Arrhenius theory. Unfortunately, in the Arrhenius theory, water will always be neutral. It's neither acid nor base. But in the case of Bronsted-Lowry acid-base, water is what we call amphoteric, meaning that it can behave as an acid, but it can also behave as a base. It kind of depends on the circumstances. So the way that we identify a Bronsted-Lowry acid or base is by using that acronym BAD. Bases accept and acids donate. And what we're talking about is protons or hydrogens. They mean the same thing because hydrogen is just one proton. So here, Arrhenius says this is an H in the front. It is the only positive ion here. So this is going to be the acid. Well, that is true. Bronsted-Lowry definition agrees with the Arrhenius definition. It just expands it a little more. So in this case, remember, acids donate their hydrogens or donate their protons. So the nitric acid is going to ditch that hydrogen and it will be left with the NO3 ion, the nitrate ion, and that is what makes it a Bronsted-Lowry acid. Now, water being the base, that is because bases accept either hydrogens or protons. And this H2O becomes H3O, indicating that it has gained a hydrogen. So that would make water, in this case, a base. Next up are a list of bases that you should name. Bases are a lot easier because they just follow ionic naming rules, which thank goodness, because the last thing we need is another set of naming rules. So here we have lithium hydroxide, calcium hydroxide, and magnesium hydroxide, all of which are metals that come from group 1 and 2. So they do not need Roman numerals when you name them. but the cobalt and the iron are transition metals. And for that reason, their names require Roman numerals. In order to figure that out, you just uncrisscross to figure out the charge on the metal. Hydroxide has a -1 charge, so there is no reducing in this case. The 3 subscripts on the hydroxides have each come from the metal, making cobalt 3 and iron 3. A heads up on the pH scale, your teacher may ask or require you to do calculations in terms of the pH equation. I don't ask my first year chemistry students to do that, but I will ask them to do things like this, which is comparing pHs in terms of hydrogen ion concentration. So to do that, fill in the blanks on these sentences. A solution with a pH of 5 is 10 times more acidic than a solution with a pH of 6. That is because each jump on the pH scale is a 10-fold difference. Getting lower on the pH scale indicates you have more hydrogen ions and that your solution is getting more acidic. And moving up on the pH scale towards 14 is going to indicate that your solution is becoming less acidic or more basic. Again, each jump is a 10-fold difference, so 2 jumps would be a 100-fold difference, 3 jumps is a 1,000-fold, and so on. Now, for the second sentence, it says a solution with a pH of 2 is 100 times more acidic than a solution with a pH of 4. That is because a 2 and a 4 are 2 jumps apart from each other, so 1 with 2 zeros, if that helps. And because we're becoming more acidic, we need to go down the scale. Here are 2 more sentences to fill in based on the pH scale. A solution with a pH of 11 is 100 times more basic than a solution of a pH of 9. In this case, we're going up the scale because we are looking for something that is more basic. We're going to go 2 jumps because we're talking a 100 times difference. So that would indicate 2 jumps. You would go from 9, skip over 10, and jump to 11. For the second sentence, a solution with a pH of 3 is 10 times more basic than a solution with a pH of 2. Yes, those are both acidic pHs, but remember, it is an acid-base spectrum, so the less acidic something is, the more basic it is. So because 2 is more acidic than 3, that means 3 is more basic than 2. Because 2 and 3 are just 1 jump away on the pH scale, this would be a 10-fold difference. For the question on indicators, we have the question, a solution yields a pink result with phenolphthalein. What do you know about this solution? And then the solution is tested in thymal blue and yields a blue result. What is an appropriate pH range for this solution? You may need to reference an acid-base indicator reference page. I know everyone uses different references for this. If you do not have one, I recommend using the one from New York State. You can just put in a Google search bar, New York State reference tables, and I believe this is table M or K, somewhere in that area. Phenolphthalein is a pretty common acid-base indicator, so this is one that I would suggest that you learn and memorize. Phenolphthalein is going to be clear in acidic solution and it will be pink in basic solution, so that will return a pink result if it is basic. And then for thymal blue, again, thymal blue is probably one that you'll need to look up, but if it is blue, then that means the pH is 9.6 or greater. It is a yellow result, I believe, if it is 7 or less. And then in between 7 and 9.6, it would be a mix of yellow and blue, yielding a green result. So in the case of our solution, because we have the blue result, it would have to be a basic solution with a pH greater than 9.6. Up next are acid-base reactions. Your task is to complete the reactions. First up, we have a single replacement reaction between an acid and a metal, which will always yield hydrogen gas and some ionic salt. So in this case, we would be left over with aluminum chloride. This is just a simple single replacement reaction. Whether you knew it was an acid reacting with metal is really not important to how you would solve that. Now, the second one on the bottom is called a neutralization reaction because we have an acid reacting with a base in equal amounts. And in that case, we would have an ionic salt form and water. And the resulting solution should have a pH of 7 or something very close to 7 if it is a true neutralization. Now, you solve it the same way you would solve any other double replacement reaction. It is important to realize that we need our reactants to be soluble in order for this to work. So this is a group 1 ion, always soluble. Hydroxides don't always love to dissolve, but the calcium hydroxide will. In this case, you would just swap partners. So you have the calcium chlorate here. Crisscross the two. Don't forget to do that. Of course, you have to balance your equations. And then the leftovers of 2 hydrogens and 2 hydroxides would give you 2 waters. I typically like to write it as HOH when I'm doing an acid-base neutralization. And that's just because it's very easy to see that we have the H and the OH. You could also write this as H2O. Either way, obviously, is correct, but I simply prefer to write it this way when I'm talking acid-base because it helps me remember that the solution has been neutralized. We have an equal amount of H canceling out the OH, neutral solution. Final question is a titration, which I'm not asking you about the process here. This is just a math question. So if you are unsure or unfamiliar with the process of a titration, I would definitely go back and check out that video on this channel to make sure that you feel comfortable with it. The question here is a monoprotic acid with a volume of 50 milliliters is titrated with 65.8 milliliters of 4 molar sodium hydroxide. What is the concentration of the acid? In order to do this, you would use the titration, or sometimes it's called the dilution equation. That would be the molarity times the volume of the acid is equal to the molarity times the volume of the base. In this case, we don't know the molarity of the acid. You could have also written M sub A to indicate it's the molarity of the acid. So we're going to multiply that by the volume of the acid. Here we have the molarity of the base times the volume of the base. You simply just do the algebra, solve for M, and we should have a 5.26 molar solution of this acid. All right, I hope you feel prepared for your acid-base test. Please leave any questions you have in the comment section below this video. The next unit on this channel will be redox, so make sure to subscribe so you don't miss it. Those can get really tricky, but it's my favorite, and I feel like I teach it pretty well. All right, I hope to see you in the next one. Bye.